welcome to InfoIndex. Today we'll be doing 1997 CAP's problem part B's question 1. So in this question, a massive satellite is in orbit. It has a rotating cuff that allows a small mass m on the end of the cord to circle about the satellite at a radius r with speed v. The initial speed of the satellite is v0, and the initial radius of the circular path is r0. A mechanism within the cuff allows the cord to be drawn in so that the radius of revolution for the mass decreases. The center of revolution for the mass remains constant, and you may assume that the satellite is much more smaller than m. So I want to find the initial tension T in the string. So we know this mass is undergoing circular motion around the satellite, right? So circular motion formula is Fc equals to mass velocity squared over r, right? And it says here, you may assume the satellite's really small, much smaller than m. So there's not going to be any not any gravitational force. So the force Fc is just going to be tension. So your tension is just going to be mass velocity squared over r. Now B. So suppose that the cord begins to be drawn in a constant rate. So r decreases uniformly, right? Express the speed v of the mass as a function of r and r0 and v0. So here, right, angular momentum is conserved. So L1 is equal to L2, right? So angular momentum of the object is just going to be its moment inertia times angular velocity, right? So here we can say m v0 r0, right? This is going to be equal to whatever your v and r is after you start drawing it in. So we can cancel out these m's. You can see, just rearrange for v. So we get v is equal to v0 times r0 over r, right? So C, if the cord snaps beyond the maximum tension T max and the radius of the satellite is r, what constraint must be satisfied in order for the mass to be brought within the satellite? So let's see. Your T max, right? This is your T max. So what I want to do is, T max from here is just mv squared over r. But you want the tension in the string to be like smaller than T max when it's at r, going circular motion at r. So you find the velocity that the mass has when it's at r. So you plug this value in when this is r. So this is equal to m over r, right? Because the radius is going to be r. And v squared, you plug this in, v0 r0 over r, and then square this, I think, because this is going to be velocity when it's at r. So this is going to be equal to m v0 squared r0 squared over r cubed, right? 2 r's here and 1 r here, right? So C is done. So what amount of work is necessary to bring the satellite from radius r0 to radius r? So I'm going to bring it from a random point out here back to the surface of here, the cylinder. So work is just the integral of force with respect to the radius, right? The distance it travels. So for this one, the force is just tension. You can write it as the integral of tension. So m v squared over r, right? dr. Now we know you're going to evaluate this from r0 to r. So this will have r0 here and r down here. So we can sub in, because when the velocity changes with the r, so we can't just take this outside the integral. So let's just sub this in. So we get the integral of r0 r m. You sub velocity in, it's what? v0 r0 over r squared, then divided by r. But here, dr. Now I can take these, this one, and this one. They are all constants, right? Take it out of the integral. Don't care about them. So m v0 squared r0 squared. Take integral. Now what we have here from r0 to r, just have 1 over r cubed, right? dr. Now we know how to take integrals, right? So this is just going to become negative 1 over r squared times 2, right? So we put the negative out front. So negative m v0 squared r0 squared, right? Now you evaluate this. This is going to be 1 over r0 cubed minus 1 over big R cubed, right? This is our equation. We can also put the negative inside to rearrange the signs. So this can also be equal to mv naught squared r naught squared times 1 r cubed minus 1 over r naught cubed. And that's it. Thanks, guys.